Thank you very much, Professor Pham. It's a real privilege to be asked to give the keynote speech in the third international workshop of the BEAS algorithm. As Professor Pham mentioned, I started working with the BEAS algorithm when it was originally developed, and I'm a firm user of the BEAS algorithm. So for today's keynote, I would like to talk about the BEAS algorithm, some of the promising improvements we have made, and also talk about some novel applications. And I'm at Cardiff University, and this is the outline of my keynote presentation. I will say a few words about the optimization by way of introduction, and also say what the BEAS algorithm is for new people who have joined, who like to know more about the BEAS algorithm. Then I will highlight 3 improvements we have made based on the local search, the neighborhood search, and how to abandon a site. I'm looking at which way to move the search. So that's the slope angle computation and hill climbing. And then a third improvement is the recruitment, which is based on pheromones. The applications of the BEAS algorithm, again, I have 3 different applications. The first one is how BEAS algorithm can be used for data mining, and the application used is for finding faults in an induction motor. The second application is deep learning, so particularly looking at CNN, convolution neural network, how to design and optimize convolution neural network using a hybrid technique, BEAS algorithm and Bayesian optimization. And the CNN will be used for identifying faults, defects in a metal SLM process. Then finally, an application based on BAs, hybrid BA, for detecting faults in 3-phase power transformers. So by way of introduction, I'd like to say that the word optimization or optimize, that was first used in the early 19th century. We all know what optimize means. Rory also highlighted what it means to the industry. We're always striving to make things better, or to make the best or most of what we have. It is an act or process of making something as good as it can be. It's also interesting what other words have been derived from optimization. Optimum, we know what it means. It refers to the amount, or it can also refer to the degree of something that is best or most effective. Not related to mathematical optimization. Another word which is derived is optimism, and that's is a feeling or belief that we want to have something good happening in future. So, so optimize and optimization are derived from the Latin word optimus, meaning best. This is according to the Merriam-Webster dictionary. I've got a couple of quotes from famous mathematicians. Euler, he said, "Nothing in the world takes place without optimization, and there is no doubt that all aspects of the world that have a rational basis can be explained by optimization methods." And also another quote says, "If you want to build a ship, don't drum up the men to gather wood, divide the work and give orders. Instead, teach them to yearn for the vast and endless seas." So for the young audience, I would say, you know, optimization history is not just important, but it is a very interesting and fascinating area, very thrilling, can be funny, and it's also full of surprises. There is a book edited by Rothschild. The title of the book is Optimization Stories. So if you are on a train journey or flying, you may want to read this book, or even as a bedtime reading. Okay, so optimization, it entered the world of looking for best solutions, and in 1984, a researcher in AT&T Bell Laboratory designed interior point method. Is a optimization technique, and even the New York Times was interested in this, and they produced an article with the title Breakthrough in Problem Solving. So we are engineers, we like to solve problems, and as we heard from our first keynote speaker, how the industry is using optimization to find better solutions. So before we dive into optimization, I want to highlight some of the things that can happen when you are optimizing. Optimization can sometimes get very slow, or it can even it can bounce around forever. So I've shown two diagrams. So in the search, when you are searching for a solution, you generally define a step size. And if you define the step size too small, then as you can see, you'll be forever searching for the best solution. If, on the other hand, if you are not patient enough, you want to search through very quickly, you increase the step size, and then you begin to bounce around, and you will never reach the optimum as well. So this diagram here, two graphs, one is a two-dimensional curve I've shown with maximums and minimums and saddle points. So in optimization, we are always searching through the search space. If only we know the function, then we can see where the optimums are, local and global. But the algorithm needs to start from somewhere, and as you will see later, how the bees will go about searching for the solution. So if it is a three-dimensional, here you have a complex surface with lots of local peaks and troughs, and it's very difficult for a search algorithm to actually search through. Depends where you are starting your search from, and how your search is going to navigate towards the best solution. So the circle here in this two-dimensional XY graph is actually the local search area, which we will refer to as the neighborhood. So you will have a predefined radius to search, and you can see this radius can expand or shrink, and this will be one of the improvements that we will make. And which way to go, the direction, you know, that is another improvement, and how to attract more bees into this search area, that's going to be the third improvement. So I want to give you a riddle to think about. So here, say you are standing in front of a wall, say you are 10 feet away from the wall, okay? And imagine that you have a magic feet, and suppose I ask you to take a step which is half the distance to the wall, okay? So how close would you be to the wall after your first step? Obviously, you will be 5 meters away from the wall. That's fine. But if I ask you to repeat this process, would you ever reach the wall? Well, you will only be getting nearer and closer to the wall. but you will always have a feed size which is half the distance. So convergence becomes a paradox. But as far as engineering is concerned, we will accept any solutions which is good enough, which is close enough to the wall. Okay, now I'm going to introduce the Bayes algorithm. It is a nature-inspired, a swarm-based search technique, which copies or mimics the foraging behavior of honeybees, which are found in nature. And the original Bayes algorithm was developed by Professor Pham and the colleagues in 2005. And the reference to that technical note is given underneath here. And also the standard formulation is described by Professor Pham and Dr. Marco Castellani. The behavior, foraging behavior of honeybees, okay, the bees will live in a hive and they have a population of bees. And the way they go about foraging is they will divide the work, the task, and the so-called scout bees will volunteer to randomly go and sample the flower patches. And they have to report back the findings, and they have to come back and communicate to the waiting bees in the hive the energetic yield of the flower patch, how far they had to fly, how easy was it to extract, and the sugar content. And they will do that by means of a waggle dance. Okay, that's a dance which is formed in the shape of number 8. Okay, they will do this, and the bees that are waiting will observe, and they will know which way to go, how far to go, and if the patch which is being advertised is promising or not, so that recruited bees can go and exploit. So there are two things which are going to happen. One is exploration and the other one is exploitation. So Bayes algorithm is a nature-inspired swarm-based optimization method. You have population of bees to start with, and you have a small number of the bees are allocated as scout bees, and they go randomly. They do the global search, and once they find promising patches, the bees will be recruited, and they will go and do a local search or exploitation. The cycle is, of course, repeated until a suitable, acceptable solution is found. So, of course, when you come to optimize, you are either going to look for a maximum solution or a minimum solution, but that's not the full story, because you will have lots of constraints and conditions which you need to fulfill. So in simple terms, okay, the algorithm will work, as I said, with a population which are randomly initialized, the scout bees, which will go and do some sampling, and they will come back and do a waggle dance. And through this waggle dance, the local search will be promoted, while they also maintain the global search. A few bees will continue to randomly explore. Okay, and all of this is done, and there will be improvements which will be made, in particular for looking at the neighborhood and the direction to move. So after they find the promising patches, they will evaluate the solutions and look if they have found the solution they want, which is acceptable or not. If so, the algorithm stops. Otherwise, it will keep continuing in a loop. Okay, the parameters that are used for the algorithm are number of scout bees and number of elite sites, best sites. So people who use the algorithm will know these parameters, and the description of all this is available on the Bayes algorithm website. So just to give you an illustration, this is how the algorithm will work. So if you had function that you want to optimize. The bees in the hive randomly, as the scout bees, will land on different positions on the curve. And then you want to, if you want to maximize, you look at the Y value for these positions and identify the best Y values. So you can draw a line and say the first 5 are best outcomes and the bottom 5 are not so good. And so you retain those, and then you define a search area around those 5 best solutions you have found, and you start recruiting more bees. So the blue squares are the best of the best. So you get more bees going in there and less bees going to the other local search areas. And then you identify the best positions you have found in each of those local areas, search areas, the red arrows. So, and then you retain the top ones, and then you discard the others, and then you repeat the process while you are also randomly sending some other bees. So you are always keeping an eye out in case there are other better solutions. And ultimately, if you keep repeating it, you will hopefully end up to the best solution. Okay, so I'm going to the second part of the talk, which is the improvements. The improvements are going to be, as I said, where to search, how to conduct the local search. So these are the local search areas, the neighborhood, and usually you begin to shrink the search area. So the arrow here pointing to the left shows the shrinking neighborhood. But what happens if you find more promising solutions within the search area? So you may also want to expand. So the arrow going out, the dotted line shows the neighborhood size being increased. So you can also abandon the site. If you don't find any more solutions, you can abandon the site. And this arrow here shows the convergence. The solutions are always getting better, and you want the search to go towards the convergence direction rather than the opposite direction. Sometimes you may have to go in the opposite direction in order to get out of a local optima. So here I have shown a curve with lots of minimas and maximas, and where you want to search, and how you can get stuck in local optimum or local minimums rather than the global. Okay, and always your algorithm should be in the direction of convergence. The promising improvements, as I said, you have to maintain some heuristics mixed with some randomness. So the AI-based algorithms and machine learning algorithms are going to use some heuristics and also mix it with a little bit of randomness. So you have a better chance of finding the most promising solutions. The traditional methods, which are very brutal, step by step, they may not always converge, and they may not always deliver the solutions that you are looking for. So the first improvement is the adaptive change in neighborhood size. So here, as I explained, so you choose the neighborhoods where the solutions are promising, and then you want to adjust the search area. If the solutions are consistently good, then you want to expand, enhance the neighborhood size. If you are finding the solutions that they are decreasing, then you want to shrink. And if you don't find any more improvements, like in this case, if it's a saddle point, it's flat, so you're not going to find anything. In that case, you can abandon. Okay, more details of this technique is in this dissertation by Arthur Imangluev. There's a lot of equations used in the way how the neighborhood is shrunk or expanded or abandoned. Okay, and again, this diagram shows exactly what I mean by expanding. So you are here in a more promising area compared to this side. If you go higher and higher, you will come to an optimum, but actually you will get stuck in a local. So it's better we shrink and discard and then try and move in the other direction. Whereas if you are here, okay, you can afford to move ahead in this direction. So finally, you can reach the global optimum. These algorithms, these improvements are tested on some benchmark functions. Himmel Blow function is a nasty function, which is got in the left-hand side, you can see that it's got lots of local optimas. And so the algorithm has to really negotiate through all these locals in order to find the best solution. So the improved algorithm in the enhanced BA was applied to find the optimum. So the standard BA, the basic BA, found the peak was 9.6, and the enhanced BA with the adaptive change in neighborhood size and site abandonment improved the solution by a little bit. Okay, in terms of time taken to solve or find the optimum, also the enhanced BA did much better than the standard BA. Okay, the second improvement is the slope angle computation and hill climbing. So again, first we saw how to adjust the size of the neighborhood search, and now we will see how to encourage the search to go in the right direction. So the problem is the basic BEAS algorithm suffers from a high level of randomness, and the computational time can be long, and it can also get stuck in a blind search or in local search processes. So the solution is to improve the local search direction. Okay, it's concerned with locating the best sites and pointing it in the right direction. So more details are found in this reference paper. So what it does is, as this diagram shows, you want to look at the local search area, the neighborhood, take the most extreme points you have, and then from that you can work out the slope. If it is too steep, okay, then that means you are a little bit further away from the best solution. If it is the angle is very small, that means you are getting closer and closer to the best solution. So here A X there, that's one peak, and B suffix X there is another peak. So the slope angle computation and hill climbing will encourage the algorithm to move in the right direction. So here it's better to move up rather than down, and here as well it's better to move up and to reach the maximum. If you're going down in this direction, or you can get stuck in the minimums. Again, this improvement was tested on the same benchmark function. The basic B found the maximum to be 9.6. The BEAS algorithm with neighborhood adjustment, that found a little better solution, but now with the second improvement with hill climbing, it improved even further. And as well, the time taken to search and find the solution with the slope angle and computation and hill climbing added to the first improvement was more effective. Now I'm coming to
Michael, you have one minute left.
Okay, so now I'm coming to the third contribution for the improving the algorithm, which is based on pheromones. Pheromones will recruit more bees to the site, and it does it by advertising the bees to come to the site more. And again, the improved pheromone-based algorithm was tested on benchmark functions, and the results improved by 41%. The applications, as I said, the first one was how to use B's algorithm for mining. Second is a combined B and Bayesian to design and implement convolution neural network. And the third is a hybrid B's algorithm to detect faults in three-phase transformers. So these are the faults found in the induction motor. The B's is used for mining. It uses two parameters, namely the quality and coverage to find the best rules which satisfy the class. Okay, and the explanation and more details of this algorithm are published in a paper, and the results, as I have shown here, B4M, B's for mining, gave overall better results. The CNN was designed for identifying pores, and before this can be done, CNN needed to be constructed with the right parameters, and for that BA was Bayesian optimization was used, and the weights were adjusted using BA, and overall the results was the BA BO CNN was tested with 3 different data sets, and the results looked promising. The third application, novel application, is the three-phase transformers. Again, a hybrid BA was used for feature selection and for the classifier to recognize and identify those faults. And the algorithm, when BA was combined with SVM, AN, and KNN, it gave better results than the GA-based method. So I'm now coming to the conclusion. So we have introduced 3 improvements which were promising. So adaptive neighborhood search and site abandonment, slope angle computation and hill climbing, and also pheromone-based recruitment. So applications, data mining using bees, CNN optimal design topology, combining BA with Bayesian optimization, and hybrid B's algorithm for detecting faults in transformers. So future work, there is still much we can do by looking at recruitment based on pheromones, and also introducing short and long-term memory. There's plenty of opportunities to enhance the BA further. And of course, as we heard before, there are endless possibilities for different applications of BA where they can be applied. Finally, I want to acknowledge all my colleagues and friends who have contributed to this work. Thank you very much.